Thank you, Simon, for a great introduction, and thanks Jesus inviting me here. It's great to see a lot of young people here and a lot of okay, and yeah, this is one of my favorite department. I have came here. I think this is the fourth or maybe even the fifth time come to visit. Okay, I've been I know several faculty like Ray Carroll, Lai Xin Wang, and yeah, several others very well. Okay. Today I'm going to talk about the statistic triangle. This is in collaboration with one of my several of my former students. Pengsheng is right now in University of Georgia. Tracy and in Harvard, and Wanshan and Shengming are in industry, okay, currently industry. Okay. Can you hear me well? Okay, cool. So this started with a data set our team recently collected. Some of you may heard about it. Okay, so this is about a large scale, high quality data set on the statistical publication. What is in here is like we have for 83,000, okay, roughly 83,000 papers published in 36 journals, spanning roughly 41 years in statistics journals. Because we started this in 2015, as you can see, so it ends in 2015 because we started there. But it takes several years to collect and clean and this data set, and it also takes a few years to analyze it. Okay. What is in there is that we take every paper. The main part is too long, so we do not download it. But otherwise, we download everything. Okay, so this is part one of the information. The second part, harder, you need to find out which paper cite which. So this you need to like do web scraping. You go to many places. The reason you have to go to many places because each website, the information they provided is always a significant fraction, like 10% is wrong or missing. So you have to go to different places. For example, in the paper in 1970s, usually they have missing DOI. Okay, but a recent paper, we all have DOI, but all the papers, they do not or missing. Okay, and sometimes authors mislabeled. For example, if you publish the annals, you publish it with full name, but you publish in GRSB, you have last name with the initial. So Fan Jie dot. Fan Jie dot can be Fan Jianqing Fan, or Fan other thing. Like D. Rubin can be Donna Rubin or Daniel Rubin. Okay, this is several. Okay, and also you can be the same author, same name but different person. We have 3 Hao Zhang in our data set. One at Purdue, one in Arizona, one in 2 Sigma. Okay, so anyway, all these problems you have to takes really long time to clean them. Okay, eventually, after all this effort, okay, we have to make it freely available to everybody. Okay, so as far as I know, as a lot of people are analyzing this, and because this is a very unique data set on us, the statisticians, I would encourage everybody, okay, if you're interested, you can take a look and analyze by yourself for yourself, okay. Clearly, there's many problems you can study. For example, in our papers, we had do journal ranking. So people always kidding about what the top 4 journals in statistics. Okay, so this data set actually verified that the top 4 are really stand out. Okay, but you can take a look. And for example, you write a paper, you wish to know 10 years after that, how many citations you get, that citation prediction, all these kind of problem, or you can have various ways to measure the diversity, like a course diversity, citation diversity, so on and so forth, all these kind of metric, okay? But for the interest of time, today I'm going to focus on 3 related problems. It's essentially just one problem, okay? What are the representative areas in statistics? You have primary areas, okay? And primary areas can also divide it into sub-areas. So therefore, how many primary areas? What are they? What are the representative sub-areas and so on and so forth, okay? And give a person, for example, Ray, okay? What is his interest in these primary areas? Okay, and what his area evolve over time for all his career, from younger faculty, junior faculty to now. Okay, so these are the 3 problems we are going to answer. We start with the CIT late work. Okay, there's several things need to explain. First of all, why not the co-authorship late work? The citation network is much more dense comparably. The co-authorship network is very sparse. Okay, but the thing is, the citation network is not symmetrical. Okay, you cite one another people, the other people do not have to cite you. Oh. So therefore it's not symmetrical. There's two ways to symmetrize it. One is a citer network, another is citee network. Citer means if you and I have age, we both cited some other person. And the citee is you and I have age if we are being cited by another people, okay? So we have constructed 21 citee networks. The time window is right here. For example, the first one is from 1991 to 2000. The last one is 2011 to 2015. The windows are not equal spaced, okay? The reason is in the 1970s or 1990s, we have fewer citations, we have fewer statisticians. So we have the window slightly larger. And the year 2015, we have more frequent citations. So we make the window slightly narrower so that they're roughly even. Okay. The first one is going to be very special. We're going to spend a lot of time on it. We use it as a benchmark. Okay. Others, we are going to use a benchmark and study the dynamic involvement of these networks. Okay. So what is the citee network? For example, in paper 1, paper 2, okay, from the text of the paper, we download the text, okay. If paper 1 and paper 2 both are cited by paper X, then they have a count of 1, okay. If paper 1 and paper 2 has been co-cited by like 100 times, then between paper 1 and paper 2, there's an age but a weight of 100. Okay, so this is the citee network. Okay, so more detail is here. Okay, we are going to make it binary. Okay, the reason is you can analyze the weighted network directly. It's fine. Okay, we have tried that, but the result is not that different compared to analyzing the binary network to be constructed now. The reason if the pick the binary network is because the binary network in theory and in method is most well studied. A lot of papers, a lot of approaches very carefully. Okay, and okay, so but the result is not that different. Okay, as I described. Okay, now you have many. Okay, you have a network. Every node is an author. Okay, okay, an author can have multiple papers, right? So you can count you and I, for example, whatever papers we wrote, okay, the number of times being cited, then between you and me, okay, there's a weight for that age. Now, you and I, you and him, you and her, you have many weight ages. If the total weight is smaller than 60, so that means you're probably you're not a frequent publisher, frequent author. You probably publish very few. Okay, so we say, okay, we are going to make your age weight to be 0. Okay, if that's a total, okay, I'm going to remove that load. Okay, I'm going to remove that load if the total weight is too small. Okay, you remove that node. Okay, and at the same time, if 2 authors, the age weight is smaller than 2, including 2, that's also too small. We think you do not really essentially have age, so you're making age 0. So therefore, this way we have a binary network. Okay, binary network. A lot of nodes are removed, and the remaining nodes, okay, is either 1 or 0. 1 means between these 2 nodes, age weight is bigger than 3, bigger or equal to 3. Smaller than 2, it becomes 0. Okay, this becomes a binary symmetric network. We call the final citee network. We do the same for all these 21 networks. Eventually, we have an intersection of 2,030 nodes. We think these 2,830 nodes are the most frequent authors, published authors in this data set across these 25 years from 1990 to 2015. Okay, so this is the data set. Any questions? Vertex is bigger than 60. We keep that load. Less than equal. And the correspond to the author only. Okay, yeah. Okay, we first delete a lot of authors if the total weight is small. So then after this process, among the remaining authors, we observe the age. If the age weight is bigger than 2, then we make it 1. If it's smaller than 2, we make it 0. No, yeah, that's a very good question. We exclude self-citations. We do not count self-citations. Okay, cool. Okay, thank you. Good. It's not. It's like 80 ways. For example, if me, okay, I've been co-cited with other 10 authors, but my weight with the first one is only 5, with the second one is only 2, and the total weight is only 60, which is a reasonable small number. So that means I'm going to remove myself. Okay. A lot of authors are much bigger than that. Okay. Bigger than 6. Okay. Okay. So this is the first cited network. We do the same process for all the 21 network. Eventually, we take the intersection and we only keep 2,830 nodes. So this is the most frequent or most prolific authors in our community among these like 26 years from 1990 to 2015. Okay. One more thing I have to mention. I'm going to present the statistic triangle using the first network. So a lot of things you may think very confusing is different from your impression. Bear in mind that's in 1990. For example, Bingyu in that triangle is very Bayesian, okay? But Bingyu now is not very Bayesian, okay? So because that's in the 1990, okay? Okay, so that's the data set, okay? In his Fisher lecture 1998, Bradley Efron has presented a triangle. Okay, so Efron's triangles looks like this following. Okay, and there's 3, according to Brad, there's 3 main philosophy in statistics: Bayesian, frequentist, and Fisher. For example, if you take Gibbs sampling is very Bayesian, right? So you take Gibbs sampler there. In the triangle, you make it a weighted convex linear combination of 3 vertices. So you have weights, right? These weights may be, okay, maybe you can say 90% of Bayesian, 5% Fisherian, 5% frequentist. Okay, so that is the weight of Gibbs sampler in Efron's triangle. Okay. The main result, one of the main results of this talk is we discover a very similar triangle, but Brad Efron's triangle is drawn by hand. Okay, ours triangle is discovered by data. Okay, that's the difference. Okay. Okay, so we discover a triangle. Okay, and we also in the spectral domain we build a research map. In this research map, okay, everybody in that 2,830 authors is a small dot in that triangle, in that map. And the relative position according to the 3 vertices of the triangle is the research interest of that author. For example, if you're right in the middle, okay, maybe your weight is 1/3, 1/3, 1/3 in according to the 3 vertices. The 3 vertices, each of them represent a primary research areas in statistics. 2 of them the same with Brad Efron, 1 of them is different, you will see, okay? And also, okay, each primary research area can be further divided into sub-areas. We are going to report 15 sub-areas, okay, you will see. Okay. And also another question is, okay, this is only for the first network benchmark, right? Benchmark is static. Then we have total of 21 network. Then for every author, for example, Ray Carroll, okay, his position in the first triangle is his research interest in 1990s. The second one maybe it's 1995. The third one maybe in 2000. You collecting all those dots in a reasonable way, in a correct way. That is research trajectory. It describes how his research interest migrate or evolve over all these years. So this is 3 things we're going to report. And the following 6 slides is going to be, 7 slides are going to be more technical. Okay, I'm going to use 2 slides to introduce the model and 5 slides to introduce the methods. Okay, it's going to be a little more technical. Then we're going to come back to the data set. Okay. So the degree corrected mixed membership model is a well-known model in network analysis. Okay. but we can use it to model this DCIT network. Okay, the data is suppose you have a symmetric binary data sets. We do not count self-citations, so the diagonals is always 0. Okay, it's a symmetrical binary matrix. The diagonal entries are all 0. We assume there are k perceivable communities. So each of these community is a primary research areas in statistics. So k is relatively small, okay, or you can say 3. Okay. And of course, the mixed membership model allows you to have sub areas. Okay. For rank k matrix omega, we assume the matrix is symmetrical. Arbitrary triangular entries of A are independent Bernoullis, but the Bernoulli parameters can be drastically different from one to another. Question? This is a mixed membership. This is a mixed membership model. Every author, they can have different ways over different areas. So it's similar to the non-overlapping network model. Okay, it allows, it is overlapping, but we do not think conceptually the research areas are overlapping. It's more like the research interest is like they have a weight vector can be arbitrary values in different areas. You will see them from the next slides. Okay. So after that, you can write A equals omega because the diagonal of A is always 0. So for convenience, we subtract omega by its diagonal. So this whole thing, okay, the diagonal entry is also 0. The other part is just the Bernoulli standardized Bernoulli's laws. For example, Aij is 1. The Bernoulli parameter is 0.3. Okay, then W corresponding is 0.7. Okay, just throw away other parts of there. Okay. So we call omega the main diagonal, main signal, and the W the noise. Okay. The omega matrix will be used frequently later. Okay. Now the later modeling, a lot of literature on how to model omega. Okay. Here we assume omega is rank k. Okay. So far it's rank k. Okay. The degree corrective mixed membership model has 3 layers. The first layer is for every author, we use a set I to model his degree. Okay, it's not exact degree, but when set I is large, it means this author is the degree is much higher. Okay, for example, Elon Musk, if he's in this level or he's not, okay, then his set I is very large than other people. Okay, and the second layer is for every author, for example, Ray. Okay, Ray, his influence or interest would be spread around these K communities. So I'm going to assign him a K-dimensional vector, pi I. So this is our main interest. Sorry. Oh, sorry. This is Ray's pi I. So K is a small k from 1 to 3, for example, 1 to 3. Then pi I1, pi I2, pi I3 are his weight in Bayesian, frequentist, and another. Okay. So this is the second layer. So by this model, you can see we allow a person have different ways, okay, in different areas, so it's overlapping. Okay. Last, you can sort of think P is a baseline collecting citation between areas. So P is very small size. It's a 3 by 3, but K equals 3. Okay, it's very small. Okay. So therefore, if you write it in matrix form, okay, you can have omega j equal to set I times set j and pi prime P pi j. So this is omega. Okay. Work of a binary graph. Degree is not two. No. It's binary. The degree means, okay, for example, if the row one, if you count the degree, you count how many ones in the first row. That's a degree. Well, work out a binary graph. Binary graph means every entry is either 0 or 1. But a row you can have yeah, okay, you have of course you have many rows and many columns. Binary just means the value is 0 or 1. Okay, so this is the model. Okay, so what is our interest? our interest is study this pi I. We want to, for every author, we want to estimate pi I, for example, raise pi I, okay, another person's pi I, and so on and so forth. But here, this one is a big nuisance parameter. Why? Because you can think about two person, okay, Ray and another senior professor. Their set I are both very large and similar. But for example, Ray and Jianqing Fan, their set I are both very large, but their pi I may be very, very different, right? This means set I similar does not imply pi similar. We are really interested in pi similar. On the other hand, think about another scenario, Ray and one of his students, okay? So their set I very different because Ray is, okay, a lot of, the degree is very high, the student is very low, a degree is very low, but their pi I may be very similar, right? So this shows our interest pi I, but the set I can be a huge nuisance parameter, okay? So therefore, how to remove the nuisance effect of set I, okay? We have to normalize. We have to normalize the data set. Okay, so conventionally people use Laplacian. Laplacian normalization is not very successful here. So we introduced a different normalization. Okay, Laplacian normalization is, okay, for the spectral approach, what Laplacian do is we first normalize, then we do the PCA, then we do the clustering. Okay, but for us, we do the PCA first, then we do the normalization. So therefore, Laplacian normalization is before you do PCA, and we are after you do the PCA, which makes it very, very different. Okay, but two steps may be combined. What we do is the following, okay? We think about the case where we do not have noise, okay? For a minute, okay, we do not have noise. So we are given this omega, okay? We are given this omega, okay? So real data is the matrix A. You obtain the leading eigenvectors. You take this ratio, okay? This formula is basically say, I'm going to divide the second eigenvector by the first eigenvector entry by entry, okay? And the third by the first entry by entry. So eventually, we have a n by k minus 1 matrix here. We call it R. So assume now we have no noise, then we can do this. So what can we say about this R matrix? Okay, so R matrix, there's a lot of theory around it. It can effectively remove the set I effect and expose the direct information for pi I. Okay, as stated in this theorem. So it's a simplex in k minus 1 dimension. So if in k equals 3, so this is 2 dimension. Okay, there's a simplex in 2 dimensions in the triangle with vertices v1, v2, and v3, such that each row of this matrix R is a linear combination of the 3 vertices, of the combination of the three vertices. And the weight vector and pi I we are interested in has this relationship. Okay. So pi is what we interest. Wi you can obtain from here. So you from Ri and the vertices, then you can compute the Wi. Then you divide this vector by this B1 vector entry by entry. Okay, then that exactly is pi I, proportional to pi I. They only different by a constant. Okay. Now let me say it again. Okay. If you have this R matrix, right now it's low noise. Okay. For example, you have about 3,000 person, 3,000 statisticians. So you about 3,000 points, 3,000 row. Each row is a point in the 2-dimensional space. You plotted them on a piece of paper, right? Then the theory dictates that all these rows fall on a triangle, okay? They will not fall outside, okay? Some of them is on the vertices, some of them inside, but no one is outside. Therefore, from this triangle shape data cloud, you can easily find the vertices, right? Okay, so this is the first step. Once you find the vertices, for example, okay, all these points are inside the triangle. So therefore, from all these points, you can find all these vertices. Once you find these vertices, you know this V matrix. Now, from the relationship here, if this is known, this is from R, you can find this Wi. Once WI is given, and is known, you just divide by B1. B1 is just one vector, okay? So all of them is one vector. Then you find your pi, okay? So this is proportion to pi. For example, okay, let me go back to here. So suppose you have a lot of data cloud, you have a 3,000 point on a piece of paper. From that, you can find the vertices. Then the vertex is given, then for example, this is ray, okay, this is ray. So this is ray's point. Then you can write his point as the convex linear combination of the three vertices. You get this number. That's his Wi. Wi divided by B1 is ray's pi. That's all. So this is the idea. Okay, so this is the main idea. But this is for the case we have no noise, right? In the real case, we need to modify slightly, but the idea is very similar, okay? So I'm going to mention two ideas, okay? Two additional ideas. This is a minor ideas. What I just mentioned, main ideas. One minor idea is, in this case, they have low noise. To find the vertices is relatively simple, okay? But in the noisy case, okay, you have, okay, you every point have a noise, okay? Then how to find these vertices? Actually, this is a hard problem, okay? It's in machine learning, in everywhere, okay? This problem is known as a hard problem, okay? So we, in our paper, we propose several methods, okay? And we have a survey paper on that, okay? So we do not discuss this, okay, in detail, okay? The other one is about Laplacian. So if you do network analysis, a lot of people will argue, why not use Laplacian? So for the normalization I just explained, using the score normalization is much more effective, but this does not mean Laplacian is not useful. It can still improve a little bit. So therefore, the idea is we are going to apply Laplacian first. Then we do PCA, then we use the score normalization. It's we use both normalization, make it slightly better, okay? Okay, okay. We are going to looking for these three big dots, but red dots. Yeah, but here, you know, there's no noise. So you have very nice triangle, everybody is inside. But in the noise version, real version, every point here, every point in green will perturb by small noise. It's the data, it's the data. Yeah, yeah, you have almost, because we have 2, 8, 30 authors, right? So we have 2, 8, 30, these green dots. You plot all these green dots on a piece of paper, you try to find the red dots. Once you find the red dots, for each green dots, you can find the corresponding WI. And from the WI, you can derive pi. That's a very good question. Yeah, I will discuss later. Okay. That's a very good question. Okay. Okay, should I move on? Okay, so the final procedure. Okay, final procedure, 2 slides. Okay, so you apply the Laplacian first. You obtain the empirical eigenvector, do the score normalization, exactly as before. Okay. You do a vertex hunting to estimate the vertices. Okay, see the survey paper, we have several methods here. The one we are going to use later is this algorithm. Okay. Once you estimate these vertices, you just mimic what we described in the oracle case or the noiseless case. You obtain from Ri hat, you obtain Wi hat. From Wi hat, you obtain pi hat. Okay, then that is done. Okay. So we have packaging and we have, yeah, if you're interested, you can just refer to there. Okay, now I'm going to discuss using 7 slides to describe the main results on the real on the data set. Okay, so first of all, we are going to estimate what are the primary areas, including how many of them, and each of them, what is it? Okay. A primary area, of course, usually consists of several, okay, sub areas. How to, okay, we also suggest there are 14 or 15 sub areas. Okay, In order to divide different authors into these 15 areas, okay, we do the following. Okay, this is our head matrix. If k equals 3, so then this has 2 columns, but on about 3,000, okay, 2,830 rows. Okay. We just apply k-means to this R hat matrix with k equal to 15. Then this splits it into 15 different sub-areas. We are going to interpret, okay, all these areas. Okay. Now the main questions, how do you decide 3 and 15? Okay, so this is most time-consuming process. Okay. Most time-consuming process. We tried from k from 2 to 15. K to 15, then for each of these k, we run this mixed score algorithm. Okay. The mixed score algorithm then show you all these simplex. For example, when k equals 2, it corresponds to a line segment. If k equals 3, then k minus 1 is 2, so the triangle, and so on and so forth. So for each of these simplex, you can compute those authors most closest to each of the vertices. We print out their names and look it through, okay? Because as a statistician, we know Jiashun, we know Ray, so okay, from those kind of information, their names pops up, okay? Because they're high degree nodes in this data set. So from this kind of information, we can decide which K is gives the most meaningful results. So this is how we decide K. So eventually we decided 3 primary area is most reasonable. And by looking at those authors most closing to the vertices, we can decide these 3 areas are base and long parametric. These are 2 vertices, it's the same as Brad-Evers triangle, but the last one is not featuring, it's biostatistics. The biostatistics has been raised very fast since somewhere like 1980s and 1990s. Now it's very, very visible. Okay, so this is not a surprise. There's a third, okay, vertices. We do the same for the sub areas. We tried from k equal to 5 to 20. Okay, we do a lot. Okay, it's like through the similar tedious process. Eventually, we decide 15 may be a reasonable number. 15 here is okay, it's not the ground truth. It's not ground truth. We are not very confident about the 15, maybe 14, maybe 16. But this 3, we are very confident. Okay, this 3, we are very confident. We think although statistics changes all these times, like new people, new papers, so on and so forth, but these 3 primary research areas are the same for the 21 circulated works, and they do not change. So here's the results. Okay. Okay, so first of all, there's a gray dots. It's not very visible, right? If you look at the computer, you can see it, okay? Because k equals 3, so that, remember that R hat matrix, right? That R hat matrix, need to go back here, okay? Here's, okay. So this R hat matrix, the dimension is, okay, every row is author, only have 2 columns. So therefore, every author is a point on the plane, right? Okay, so the is in gray. You probably not very visible, not very, but everybody is on there. Okay, everybody is on there. Okay, then from these dots, we can estimate the vertices. Okay, so vertices here, vertices here. Okay, now then we apply k-means with k equal to 15. We divide them into 15 sub areas. So these kind of separating lines are decided by the k-means algorithm. So this is the k-means algorithm. Okay, it's called the Vorloi diagram. Okay. Now, in each of these sub areas, we print out the name of the 5 authors with the highest degree in that sub areas. Okay. Then you can have a look from here. Okay. So these are the people has highest degree in this area. Then from it, okay, we can tell what kind of research area there. If you look at their website and their papers, you can conclude this one is doing kernel estimation. Okay. I need to remind everybody, this corresponds to the first network, which is the window is from 1990 to 2000. Okay, so this is 990. Okay. So moving to this way, you have wavelets. You have Donahoe, Johnstone, and okay, Tinterenton, Dominica Picard. Okay. So this another thing is this is about cite. It's about citation. It's not about how many papers published. It's about okay, more interest or influence. Okay. So so their work is because wavelets as an area is at the boundary of statistics, engineering, and also applied math. So there is not a surprise they're kind of on the edge, okay, not in the center. Okay. Moving to this way, you have okay the decision theory like Lawrence Brown, okay, and for Lawrence Brown and others. Okay. Moving to this way, moving to this, you have the Beijing. Okay, this is the Beijing. Okay, this is the Beijing guy. Okay, and this is my colleagues like Robert Cass, Joseph Caden, and Larry Wasserman. This Adrian is in University of Washington. This is the Beijing. Okay, we have several Beijing areas, but from this way, they become more and more computing, more computational oriented. Okay, so these five, okay, they're not statisticians, they're physicists. Why they are there? Okay. There are five physicists because in the 1990s, there's a hot area called Monte Carlo Markov chain. And there's a word called annealing. Annealing means you have a piece of metal, you heat it to 500 degrees, then put it back to water, right? To cool it down. Annealing means cool it down. So when people run Monte Carlo Markov chain, they use this terminology of annealing, and those authors frequently cite the papers by these physicists. Okay. So these physicists, why are they there? Because the people cite them. And why they're at the corner? Because in statistics, they're outsiders, right? To our area, they're kind of outsiders. So their influence is focused on that area, not too much on biostatistics, not too much on lumpermetric. So they are in the corner. By the way, where do you prefer to be? In the center or in the corner? Your high degree, if your name shows up here, you mean your degree is high anyway. But where do you prefer to do if you have a choice? You prefer to be with Ray, right? So Ray is in the center. In the center, what did it mean? It means your weights spread out in these three areas or more spread out. Okay, you're not only influence one area. For those physicists, they are only influence that is particular Bayesian area, but they have no influence in biostatistics and numeric. Okay, so moving this way, we have okay, then we have 11, we have, okay, the base, and 12, we becomes longitudinal data, okay, longitudinal. So load that Lorman-Breslow is here. So this is a GEE, general estimation equations, okay? So one of his students, Xihong Lin, and in next slide, I'm going to show Xihong. So Xihong graduated from with as a PhD as Lorman-Breslow. So her career starts from here, okay? And moving to 13, we have longitudinal data. Moving to here, we have epidemiology, and this has clinical trials here, okay? And in the center, we have the core, okay? The core, we have lumpermetric core, okay? Lumpermetric here, we have Peter Hall, Jianqing Fan, James Merrill, okay, David Rupert, Wolfgang Hurdle. And here we have Ray, Bradley Efron, Robert Ronnie Trevor, and Matt Wang. Matt Wang is the first student, Peter Hall, okay? So you can see they are right next to it. These two are right next to it. So why the clinical trial is here? Clinical trial, of course, in cancer study, they must be in the center, okay? But here, because our journal is 36 journals of primary statistics, so they are sort of on the corner. So this is the first result, okay? Any questions? Okay, here is this one is for the benchmark network. It's just one network. Okay, it's for the first network. We have 21 of them. Now for the trajectory, we are going to okay, for each of these 21 network, we can do the same. So for example, you observe Ray. Okay, on the first network, he's a dot. On the second one, he's also a dot. On the third one, he's also a dot. Could you just collect all these dots, 21 dots? That's his trajectory? No, you cannot do that. Why? Because for different network, you do have the same triangle, a similar triangle, because the primary research areas, the number do not change over the years. We believe it's still 3. So you still have this triangle, but for different network, because the sine theta theorem in the statistics we know, in the spectral domain, if you talk about eigenvectors, there's always a rotation there. There's a very nuisance rotation there. So therefore, for the first network, the second network, the three vertices are not aligned well. Okay, the first thing you do, you need to do alignment. But once you make these alignments done, then the first dot of ray, the second dot of ray, you click and then becomes now a very smooth curve. Okay, so that's his research trajectory. Okay, so the details here, technical detail. This is basically, we are going to use the projection to align rays pi I from these 21s network. Okay. Now here's the result. Okay, we have 21 of them. For each author, our algorithm embeds this author at a point in the statistic triangle. We collecting them, or we align the vertices, we're collecting them, that's a trajectory. Okay, we're going to show a whole bunch of trajectories for a whole bunch of authors. Okay, first let's go back to these slides. Do you see this small yellow box here? Okay, this one. For video effect, I'm going to zoom in to this yellow box. Okay. So this is the zoom in version. Okay, zoom in version. Now it's much bigger. Okay, now I'm going to play the video. Okay. So okay, you see how the research interests of these people change. For example, Larry, my colleague, the Bingyu, and Xi Hong and Xiao Limong, their research interests change, okay, quite a lot among this time. Okay. Okay, so this has everybody has a 22 points. Every point correspond different network. Okay, now I'm going back here. Okay, I need to put how to make it. Okay, well, yeah, a full screen. Yeah. Okay, cool. Thank you. Okay, so this is what this trajectory look like. Okay, let me explain a little bit. Okay, for example, okay, so where's the core? This is the core, right? This is a core. Okay, what's the core interpretation then? Because this is from 1990 to 2015. So one of the major movement in that time is high dimensional data analysis. Right? So for example, before we have long parametry, we have a lot of things, but a lot of people migrate to so-called high dimensional data analysis, which is like a variable selection, lasso, multiple testing, FDR, all these kind of things. Okay. You can see, for example, Bing. Okay, Bing in the 1990s. She was a graduate. I think he got her PhD in 1990. Okay, so she has been postdoc with Yale, and but a lot of her citations are from the Beijing community. Okay, so therefore, from the 1990s, her research interests or from his citation start from here, but she migrated to here. Okay, she migrated to here. Jun Liu did his PhD with Win Wang. So he's started with a guy with Monte Carlo Markov chain, right? He has a very influential paper in that. But over the years, he has traveled. Okay, I think this is Jun. Okay, this black one is Jun. He traveled to Korea. Okay, Xi Hong got her PhD from Norman Breslow in GEE. Okay, then over the years, okay, she traveled here. So she in the 2000 something, 2008, I think she published several papers in like a Danzig oscillator, comparison of lasso, and the Danzig oscillator, all this kind of thing. So that belongs to the high dimensional data analysis. Okay. And Larry was started as, his undergraduate is a computer scientist, okay. In statistics, he's my colleague, by the way, okay. So he started with Beijing, okay. So I heard, okay, over the years I heard somewhere, okay, in the 1990s, somewhere, okay, he becomes belongs to Beijing, okay. Okay, I heard from other people, he belongs to Beijing, so he does not want to undo a whole bunch of non-parametric high dimensional thing. So you can see Larry also changed quite a bit, okay, over the years. Okay, Larry, I think this curve, okay. So these are the people who has, okay, a similar, they all migrate from their area to the core, okay? Xiaoli is different. Xiaoli is also changed quite a bit, but his direction is going this way. This is Xiaoli, he going this way, okay? He's start from here, he becomes more basic, okay, according to the curve. There are a lot of people, they are not changed that much over the years. Why? It's because they are already in the hot area. Okay, they don't have to change. For example, you can see Peter Hall, Jianqing Fan, Peter Biko, Robert Bishrani. So they are already in the core. Okay, they are already the Lasso variable selection guy. So when the high dimensional arrive, okay, they still stay there. They do not change to other places. Similarly, for example, Zhi Liangyin and Dan Yu, they are in the kind of like a high dimensional and biostatistics interface. Okay, these are the epidemiology guy and also this survival and this Cox model person. Okay, they're stay there. Okay, Dan Rubin, people will say, okay, why Dan Rubin is there? Dan Rubin is there because he is EM algorithm paper. Okay, EM algorithm paper got a lot of citations. Okay, similar. Okay, not that particular paper, but work on email algorithm. So that paper has a lot of citation. So therefore, according to that, he belongs to here, but he's not at the Bayesian color as one might imagine. Okay. Okay, how much time? Okay, yeah, that's about right. Okay, okay, so this is the main result. And so one may ask, okay, so this is late work. Okay, if my area is not about late work, why should I care about this? Okay. That's a good question. Okay, the thing is the simplest structure is not only for lateral data. Okay, it actually has something to do with non-negative matrix rather than the network. Okay, the network is one type of non-negative matrix, but we have many others. For example, the single cell data. Okay, and the image data. Okay, you can always treat them as a non-negative matrix. So therefore, if your matrix can be decomposed as noise plus a signal, and the signal matrix is non-negative and no rank, you still have this kind of simplex structure. Okay, so for example, in even single cell data, you have this similar, we still have this simplex. And this simplex, what advantage here? You don't, okay, this pi I are so-called latent variable. So traditionally, how do we deal with latent variable? We use EM algorithm. The problem about EM algorithm is slow. Okay, the computing very slow. So this one shows you a simple structure. Using this simple structure, you can really compute things much faster. And there's a series there, okay, tells you this is, you have a theoretical guarantee. Okay, so this is about the extension. Okay, so if you have a non-negative matrix, you can follow this idea and figure out, okay, the simplest structure there, and use the simplest structure to derive the quantity interesting. I'm going to use just quickly a few minutes to go through the series. Okay, the series is very, very long, so I'm going to take, okay, a small part out of it. Okay. For the theoretical setting, basically, okay, we first we need some mild balanced community conditions. For example, different communities, their size are similar, and all this okay, similar. And the network is not extremely sparse. If the network is extremely sparse, then the whole network is nearly black. You have a zero, almost zeros everywhere. Okay, so you should exclude that. So these are the two main conditions. And compare the literature, because in order the procedure really works for the real application, you have to allow weak signals. Okay? In network, the frequency is weak signals. Okay? After that, okay, these two main conditions and the remark. Okay, then the loss functions decided by pi hat minus pi I. Okay, L1 norm, because pi I itself is a weight vector. So L1 norm is more natural than L two norms. Okay. The permutation is important here because this is a latent variable estimation. So it's more like a clustering. So estimate cluster may be not right labeled or aligned. So you need to permute this k of them, a k community of them. Okay. Now the short message is, in a simpler case, where all these set i's, remember the set I is the degree parameter. If all these set i's are at the same magnitude, just this is a simpler case, then our estimator of mixed score is optimal up to a root n factor. Okay, the rate here and the rate here is the same. Under this condition, this become constant. So these are the same up to a root log n factor. Okay, so therefore this is optimal. Okay. In more recent paper, Tracy, one of my former student, Tracy, and her postdoc has extended to the more general case. Why we care so much about general case? Because this is about the real data. The real data, you can clearly see race degree may be several thousand, and the fresh PhD may be only one. Okay, so you have to develop the theory to this case so that the set I can be really flexible. Okay. In this more difficult case, we also have this optimality up to this root log n factor. Okay. Remember, in this spatial case where all the data on the same magnitude, we return to the previous slides. Okay, so this reduced what the previous slide. So the short message is, okay, this procedure mixed score actually is optimal. Okay. Now here's a little bit more insight. The insight is, what's the accuracy when you try to estimate all these pi? This pi, the accuracy depends on your set I. When your set I is large, then the accuracy is very good. When your set I is very small, you have very little age with other people, so your estimation error is pretty large. For example, if your set I is very small, okay, so this is almost like I estimate your pi of anything, I fail anyway, okay, I fail anyway. So this error, because L1 norm of this is 1, so this is at the magnitude of 1, okay. Now, when degree is very high, you can beat the 1 over root n, you can achieve the 1 over root n rate, okay? But you cannot be infinite faster. In between, you gradually improve until you hit this flat rate. Okay? So the technical detail is, what's the technique you need? You basically need to do very careful eigen analysis and entry-wise eigen analysis, okay? Basically, you can say, okay, to bound this pi and its target, you can, okay, use Ri hat. And use this Ri hat comes from eigenvector. So you need to, for all these eigenvector, you have entry-wise logic division bounds. And the technique is very recently called leave one out rule. Okay, it can give it a very sharp bound. So for example, there's a lot of recent works by like Jiashun Fan and co-authors, but our setting is much more complicated because Jiashun's setting, the set I are the same. Okay, our settings, set I's can be like thousands times different. Okay? It's tending to infinity, ratio tending to infinity as it goes infinity. Okay. I think I'm going to stop here. So this is take-home message. So we have a present MAD-STAT. It's very easy to see a MAD-STAT data set, large scale, high quality on the publications of statisticians, and is free to you. Okay. And the degree correct mixed membership is a simple and realistic lateral model. And we propose mixed score as a and simply structured estimate it. And we discover a statistic triangle, research map, and the research trajectory. Okay. So for the data set, you can follow this link. Okay, it's free. Or you can go to the journal website of this paper. This is a smaller version published a few years earlier. Okay, it only consists of 4 journals, 10 years, much smaller. For the methodology, you can, okay, this paper, and this is survey paper on score. Okay, okay, thank you very much.